NVIDIA's Robotics Research and Development Digest, R2D2, has spotlighted 3 of the most advanced AI workflows and datasets designed to push the boundaries of robotic manipulation. Among them, the third entry, Dexter RGB, stands out for its breakthrough in dexterous grasping using only stereo RGB input, achieving impressive zero-shot sim-to-real performance. Trained entirely in simulation using NVIDIA's Isaac Lab, Dexter RGB enables robots to manipulate novel objects in dynamic environments with unprecedented precision. A striking demo involved a collaboration between Boston Dynamics and NVIDIA, where the Dexter RGB system was deployed in the Atlas MTS robot. The robot showcased its ability to handle both lightweight and heavy items using its 3-fingered grippers. At the core of this capability is Dexter RGB's 2-stage training pipeline. In the first stage, a teacher policy is trained in simulation using reinforcement learning, leveraging geometric fabrics, a vectorized control method that defines motion in terms of joint position, velocity, and acceleration. These fabrics also embed safety behaviors like collision avoidance and goal reaching directly into the control policy. An LSTM layer within the teacher policy enables reasoning about physical interactions, allowing for smart corrective actions such as regrasping and failure detection. In the second stage, the teacher's knowledge is distilled into a student policy using imitation learning on the Dagger framework. This student policy operates using only photorealistic stereo RGB images, learning to implicitly infer object positions and depth, no explicit depth sensing required. In practice, the Atlas robot demonstrated not only successful grasping but also emergent retry behaviors, showing the system's ability to self-correct in the event of failure. Coming in at number 2 is Dex-Mimic Gen, a system that is transforming bimanual manipulation by significantly reducing the number of human demonstrations needed to train robots. This approach enables the generation of large-scale trajectory datasets from only a small number of human inputs, making it far more efficient than traditional methods. Dex-Mimic Gen directly addresses the data scarcity problem that often hinders imitation learning for humanoid robots. It employs a real-to-sim-to-real training pipeline that begins with a human demonstrator performing a task using a teleoperation device. From there, the system augments these real-world demonstrations in simulation, dramatically scaling the dataset. For example, Dex-Mimic Gen was able to generate 21,000 simulated demonstrations from just 60 original human inputs. Once the augmented dataset is created, a control policy is trained using imitation learning techniques. This policy is then deployed to a physical robot, enabling real-world task execution based on the simulated training. Dex-Mimic Gen is designed to handle the full complexity of bimanual tasks, which it categorizes into 3 types: parallel, where each robotic arm performs independent actions; coordinated, where the arms work together synchronously, such as when lifting a large object; and sequential, where the task follows a specific step-by-step order, like moving a box and placing an item inside it. To ensure precise execution of these tasks, the system incorporates asynchronous execution, synchronized control mechanisms, and task ordering constraints. The effectiveness of this method is evident in the results. Robots trained using Dex-Mimic Gen synthetic data achieved a 90% task success rate, compared to 0% when trained using only the original human demonstrations. Finally, taking the number 1 spot is GraspGen, a massive synthetic dataset designed to advance the future of robotic grippers. Available now on Hugging Face, GraspGen contains over 57 million grasp examples for 3 different types of grippers: the Franca Panda robotic hand, the 2F140 industrial gripper, and a single contact suction gripper. All of this data is generated entirely in simulation and includes 60 different gripper transformations along with success labels for a wide variety of object meshes. GraspGen directly tackles the challenge of data scarcity in robotic manipulation by automating large-scale data generation. This approach not only saves time and resources but also allows for the creation of datasets that are both large in volume and diverse in content. As a result, robots trained on GraspGen can handle a much broader range of objects with increased precision and reliability. Each gripper in the dataset is suited to different applications. The Franca Panda excels at delicate tasks, the 2F140 is built for heavy-duty industrial operations, and the suction gripper performs best on smooth, flat surfaces. By providing a standardized and high-quality dataset, GraspGen empowers researchers to develop more generalizable grasping models that can be deployed across various robotic systems and environments. Foundation has just unveiled new footage of its Mk1 robot, Phantom, demonstrating strikingly human-like movements. This lifelike motion is credited to their innovative vision-based approach, which relies on cameras rather than traditional sensors. According to the company, conventional sensors often introduce noise and errors that make accurate prediction and control more difficult. Cameras, by contrast, offer a superior cost-to-performance ratio and deliver clearer, more reliable data, improving the robot's decision-making. In earlier versions of Phantom, torque sensors in the feet were used to measure ground interaction forces. However, these sensors introduced noise that hindered performance and stability. To solve this, the team eliminated those sensors entirely and instead adopted reinforcement learning. This enabled the robot to refine its movements through trial and error, free from noisy data interference. A key enabler of Phantom's natural motion is its proprietary cycloid actuators. These actuators feature low backdriving torque, meaning they require very little external force to move, allowing for smooth, intuitive physical interactions. Their low inertia enables rapid acceleration and deceleration, contributing to agile, fluid movement. Operating at a high bandwidth of over 100 Hz, the actuators respond quickly and precisely to commands, without relying on extra sensors or complex software to maintain compliance. Phantom also utilizes open-loop force control, a technique that applies predefined torque commands without continuous feedback. The applied torque stays exceptionally low, under 1 Nm, which means the robot can be safely and easily interrupted or redirected by a human, improving safety in human-robot interaction. The robot walks at a speed of 1 meter per second, stands 5 feet 9 inches tall, and features 19 degrees of freedom in its upper body, allowing for expressive and adaptable motion. Next, we've got Figure Helix. This robot is a game-changer, using a vision-language-action VLA model that integrates perception, language understanding, and learned motor skills to take humanoid robotics to the next level. The beauty of Helix lies in its dual-system architecture. System 2 handles high-level goals, while System 1 manages quick, real-time movements, making it both thoughtful and fast when it needs to be. Helix excels in full upper body control, allowing it to move its wrists, torso, head, and even individual fingers with incredible precision. Thanks to a unified neural network, Helix can perform a variety of tasks, from picking up objects and operating appliances to collaborating with other robots on complex tasks. It's the ultimate in multi-robot teamwork, where robots can work together seamlessly, even when handling unfamiliar objects. Helix has shown incredible prowess in logistics, like package handling and sorting. Its stereo vision allows it to understand the 3D world, making it a master at manipulating objects of all shapes and sizes. And with the addition of Sport Mode, Helix can work faster than ever, completing tasks with a level of dexterity that outpaces human ability. Talk about efficiency. Next we have Sanctuary AI, Phoenix. The Phoenix represents the next generation of robots designed to mimic human-like intelligence through Sanctuary's Carbon AI control system. This system simulates human brain functions, such as memory and sensory perception, allowing the Phoenix to perform a wide variety of tasks across many different applications. Standing at 170 centimeters and weighing 70 kilograms, Phoenix has full-body mobility and human-like hands capable of fine motor skills. It can carry up to 25 kilograms and adapt to a wide range of tasks, from assisting with daily chores to performing complex interactions in various environments. Phoenix can be piloted directly, operate with pilot assistance, or function autonomously with supervision, offering seamless integration into human teams. Its versatility, along with its symbolic and neural reasoning capabilities, make it an efficient and adaptable solution for workplaces of the future.